Hi folks, we are on our last example problem for the chapter, and this is a banked curve problem, which is a little tricky. It's a little tricky. The problem states you speed around a banked curve at a constant 20 meters per second. The road has a 15-degree bank to it, and the curve has a radius of 70 meters. Assuming that the car has a mass of 1,200 kilograms, what is the coefficient of friction between the road and the car? So again, almost just every single time we are just starting off by drawing a picture. I have a little bit of nifty technology to kind of help me out here, but I want to have my car enter this curve and leave this curve is kind of the general gist of this. I'm going at a constant 20 meters per second the entire way through, 20 meters per second. And what we're saying is that there's some radius here of 70 meters. So that's kind of a top-down view of what's going on, right? If I think about a side view, or maybe a rear view, thinking back to the go-kart scenario where we have a camera just kind of following our go-kart. In this case, it's a car, but the idea is still the same. That is not 15 degrees, but 15 degrees is pretty small. It's hard to kind of draw that correctly. So this is a stand-in for 15 degrees. We're going to draw our little car here, skinny car. Brake lights. You can gussy it up as much as you want. But at the end of the day, right, we have this rear view as we're going through the curve. So we got a top view, we got a rear view. I think we can probably start drawing a free body diagram at this point. Free body diagram, we probably want to use our rear view as inspiration and kind of draw it from that, angle, from that viewpoint. So, I can draw this a couple different ways. Let's draw just our car here as a dot. The easy force, right? Our easy force to remember is always going to be gravity. It points straight down, mg. Our normal force, right, is going to be at some angle here. Call it Fn. And then, I should probably have another force. Probably going to have friction. I mean, what is it asking us? Coefficient of friction. I need friction. So now I need to basically ask from our rear kind of vantage point, how would I describe the possible motion of this car? Well, I would say that the possible motion of this car would probably be up our ramp here, right? I would want to drift out of my circle. Generally speaking, I don't fall into circles, I drift out of them. I want to go in straight lines, right? That would imply I have some friction actually pointing down my slope. It's keeping me kind of in this. Now, in the past, we've already said that it might be convenient to kind of draw my y prime axis and my x prime axis. But there's a sticky little situation here. If I draw the x and y primes, what I'm kind of forcing myself into is saying that my A net needs to be along the x prime or y prime direction. Is that actually what's going on here? Am I actually going to accelerate down the slope? I mean, I don't think so. I think what I'm actually going to be doing is having a net acceleration directly into the center, right, kind of over here of my circle. In other words, I'm not going to be, let's do that. I'm not going to be doing this weird, like, kind of tilted axis orbit here into the road. Like, I'm not going to go into the road, eventually, dropping in altitude, right? That doesn't quite make sense when I think about my path that I will take, right? Instead, what I'm probably going to do is do something like that, right? Where I'm actually just rotating around this banked curve, but in a horizontal plane, not in a tilted plane. So this y prime, x prime coordinate system is actually probably actually really not useful for us, right? I want my net acceleration to really only be in one and only one direction. So let's kind of touch up our free body diagram again. So instead, I actually do need to kind of keep the regular x and y axes. As much of a pain in the butt as this is going to be, a net, as we just kind of figured out, a net is only in the x direction. Or I should say a centripetal is only in the x direction. Ugh. All right, so that means I'm going to have some fnx or fny as I'm writing it here, and then fnx here. Kind of zoom in a bit. That also means I'm going to have some, let's do turquoise, some ff and I'm going to have some ffy. And mg, lucky enough, is the only one that's actually in y and x itself, inherently. So the last thing we need to do is just quick, since I'm so close, let's drop the weight. I need to draw this angle and this angle. These two angles, much like the way that gravity normally kind of has some sort of angle, I'm going to draw a faint line this way, right? Normally, if we tilt the axes, this angle is always going to be whatever the bank angle is. Well, as it turns out, our bank angle of 15 degrees is also this angle and this angle. So both of these angles are now 15 degrees. Okay. Cool. Let's start summing up our forces, right? Sum up our forces. Let's do y first. We know that we're not going to actually accelerate up or down. We're actually just accelerating in the x direction. So the sum of the forces in the y direction have to be 0. We can kind of say that right off the bat. And I know that fny has to be then equal to mg plus our frictional force in the y direction, right? If I start to kind of substitute this in a little bit, I can say, so again, we're saying that fny equals all this other stuff. I can say that fn, the magnitude of the normal force, is equal times cosine 15 degrees is going to be equal to then our mg plus fn mu times sine of 15 degrees. Notice that we're taking one angle here relative to the vertical, one angle relative to the horizontal. That's why we're using two different trig functions for this. Okay, so I can actually consolidate my normal force and divide by the sum of the trig functions then that I'm able to, get after I factor out fn. Yeah, fn equals our mg divided by the quantity cosine of 15 degrees minus, I guess there's this mu in here, sine 15 degrees. All right, so we have an expression for Fn. Now it's time to look at the the x direction, and kind of just scrolling back up to our picture here. There are only two forces in the x direction. I have my normal force component in the x direction, and then I also have my frictional force as an x component equals, it doesn't equal 0. I do need some net acceleration, this centripetal acceleration. So m ac, let's just call it something quick like that. Okay, now if I write this out, I have Fn times sine 15 degrees plus my Fn mu times cosine of 15 degrees equals mv squared over r. So now at this point we want to substitute our Fn in to this equation. And it gets messy fast, folks. I'm just going to let us know that. Now mv squared over r equals, I have mg over cosine of 15 degrees minus mu sine 15 degrees times sine of 15 degrees plus that whole thing again, mg cosine 15 minus mu sine 15 times mu times cosine 15 degrees. And there's some kind of funny business that you can do here, kind of rearranging some values and getting rid of some of the terms. I suppose the way I would probably do it is everything has a mass in it, right? If we zoom out a little bit, every term here has one mass, so maybe we just cancel the masses. Nothing really. I could throw the r and the v squared on the other side, I suppose, and then everything has this denominator. So maybe if I throw that on the other side, I can factor that out, throw it on the other side, I get what? Cosine of 15 degrees. I might have to actually move over a little bit, but cosine of 15 degrees minus mu sine 15 degrees equals, and then again I'm saying g times r over v squared times sine of 15 degrees plus, again, gr over v squared times mu cosine 15 degrees. I can isolate the mu terms here, throw this guy on the other side, consolidate, pull out a mu. That step is starting to look like cosine 15 degrees minus gr over v squared times sine of 15 degrees equals, and again I'm going to factor out these mu's, these common mu times sine 15 degrees plus gr over v squared cosine 15 degrees. And then all that's left to do is to divide both sides by this term. One last step, mu equals, we're going to say cosine of 15 degrees minus gr v squared sine 15 degrees all over sine of 15 degrees plus g bar p squared cosine 15 degrees. Woof. All right. So when it's all said and done, we can plug some numbers in. We know the speed, right? We know v. V is going to be 20 meters per second. We know r is going to be 70 meters. We know the mass. Actually, the mass canceled out a long time ago. Gravity is a constant, and then cosines and sines of 15 are easily just plugged into a calculator, and you get 0.27 as your coefficient of friction. So this was messy. This was a messy problem, and I kind of warned us about that. Banked curves are kind of messy, in part just because we are not, we have to break up a lot more of our forces into x and y components than a normal banked problem. But that's because our centripetal acceleration really is horizontal. It's in the x direction, not in some x prime direction as we've kind of drawn it. And really it's the r direction, not an r prime direction. We're calling it an x and y just based on this rear tailing picture that we drew. But if we're tailing from the rear here and always kind of looking at this back rear view, really that's the AC is going to be in the R direction, the inward direction. I suppose it's negative R. So that's a banked curve problem. Hope you followed through. Let me know if you have any questions going through this, either in an office hour or through email. Sorry this was a little bit longer of a problem, a little bit longer of a video, but I really think this was a good problem to walk through step by step. All right. I'll see you in recitation then. Have a great day.